I would like to talk about the torsion-bar antenna. It is for low-frequency gravitational wave detectors. Some of you may know already, but I would like to introduce about this new possibilities. And here is the outline. I will talk about a little bit about gravitational wave astronomy and cosmology as an introduction, and then I will talk about the principle of TOBA. And then we already developed some prototypes of TOBA, so I will talk you about that. I will show you them and its results. And now we're proceeding to the next stage. So I will talk about the next plan of our experiments. So what we want to do is astronomy with gravitational waves. So since Weber has developed the resonance bar, we are trying to detect the gravitational waves directly. The resonance bar has its sensitivity around kilohertz, and its main target is pulsar. And now our mainstream is interferometer, as you know. We have LIGO in US and Virgo in Europe, and also we're constructing CaJAGWR in Japan. And they have good sensitivity around 10 Hz to kilohertz. So their main target is supernovae or neutron star binaries or pulsars. And much more frequencies. We have pulsar timing or Doppler tracking. They have good sensitivities around microhertz to megahertz. And their target is a stochastic gravitational wave background or supermassive black hole binaries. Between them, we have LISA and the CaJAGWR, but it is not launched yet. But here we have very interesting targets. For example, one is intermediate mass black hole binaries. Some says that we don't know how black holes evolves to the supermassive black holes in the center of the galaxies. So some says it's because of the acceleration, but some says it's because of the merger of black holes. So if we can detect the intermediate mass black holes binaries, so we can reveal how the galaxies evolved. And also, another interesting target is a stochastic gravitational wave background. As you know, the stochastic gravitational wave background represents how the universe was just after the Big Bang. So it reveals how our universe evolved. So these are very interesting targets, but this region is unexplored yet. So our target is here. But how TOBA can explore that region? I will explain its principle. TOBA has two bars suspended at its center, and these bars will rotate differentially by the tidal force of the gravitational waves. Let's compare to the interferometers. If the gravitational wave comes, the position of free masses will change like this. So interferometers can see the change in its arm length, its strain, and the amplitude of the gravitational wave is proportional to the delta L. L is the length of the arm length. Delta L over L. And for TOBA, we connect the free mass to the other free mass on the other side. Then the bar will rotate like this. So we can see the gravitational waves as angle perturbation, fluctuation in angle. The amplitude of gravitational waves is proportional to its angle. And interferometer's observation band is around 10 to 1 kilohertz. It's because their sensitivity is limited by the seismic noise, because the test mass is suspended as a pendulum, so its resonant frequency is about 1 hertz. So below 1 hertz, the sensitivity is limited by seismic noise. On the other hand, TOBA is suspended as a torsion pendulum. Its resonance frequency is very low, like a few millihertz. So the seismic noise is reduced, and TOBA has good sensitivity around 0.1 to 110 hertz or something like that. And the advantages in interferometers is that they have high sensitivity because they have long baseline, like 3 kilometers, so they are very sensitive. TOBA is not so sensitive as interferometers, but its configuration is very simple and small and inexpensive. That's our advantages. So here is a fundamental noise of TOBA. This is the sensitivity example. When the test mass bar length is 10 meter and test mass and suspension is cooled down to 4 Kelvin because of the thermal noise, reduction of thermal noise. And at higher frequency, sensitivity is limited by shot noise, and lower frequency sensitivity is limited by radiation reflection noise. When compared to other detectors, it's like this, and this sensitivity is almost as same as the CaJAGWR one, so it bridges the interferometer's band and laser band. This is how long we can see for the black hole mergers. This is the x-axis is the total mass of black holes, and y-axis is how far we can see the black hole mergers. So we can see the black hole mergers with the 10 to 5 solar mass black hole mergers to the distance of 10 gigaparsec. It means that we can see the black hole merger at almost the whole universe. And another target, a stochastic gravitational-wave background. Sorry for, again, this notation again for people in the LIGO seminar. So this is the previous work. The x-axis is frequency, and y-axis is the energy of the stochastic gravitational-wave background. So with TOBA, when we used 10-meter TOBAs, 2 10-meter TOBAs, and we observed 1 year and performed the cross-correlation analysis. This upper limit will be like this. This is below the theoretical limit, BBN. BBN means the theoretical limit according to the nuclear creation or kind of things. And this is what we can do for normal TOBA. But we have another option as rotating TOBA. If we rotate the detector, the gravitational wave signal is up converted. So low frequency gravitational wave signal appears at around 2 by omega rod, and the angle perturbation is like this. So we can avoids low frequency noise, and also we can expand the sensitivity range to much lower frequencies.
So what sets the basic low frequency? Is it the resonant frequency of the suspension? Or?
For normal TOBA, the
Yeah.
sensitivity is limited by the, it's kind of, the resonant frequency is big issue, but the rotating frequency, it doesn't matter whatever you want.
Mm-hmm.
It depends on what frequency in what frequency the detector is sensitive.
Sorry, just what's the physical mechanism for getting it to rotate?
You just rotate the detector, hold the detector. I will show you the prototype as a rotating TOBA. It's the it's
Is this a satellite?
the satellite. It was satellite. In the prototype was satellite, but
Oh, I think this was suspended.
it's suspended, and we just if you want to do this on the ground, you just hold the mechanism, like both opticals and
Doesn't the
bars.
suspension fiber get very twisted eventually?
Yeah, but you can rotate the suspension point also. So this is a sensitivity for rotating TOBA when we rotate the detector with rotation frequency as 5 by 10 to minus 5 Hertz. The frequency, the sensitivity is like this. It reaches pulsar timing band and Lisa band. So we already developed some prototypes of TOBA. So I will show you them. One is prototype TOBA on the ground. We have small 20 centimeter bar, and very characteristic technique is suspension. The bar is suspended by the magnetic levitation. The test mass is suspended by the pinning effect of the superconductor. And its rotation is monitored by Michelson interferometer. And here is the setup. This is the vacuum tank, and we have test mass here. And here is a superconductor, and this is rotated by its magnet, and it's this superconductor.
What's the configuration of the Michelson interferometer?
This is just, I will show you
Okay.
the picture. It's hard to see, but laser is coming from here, and here we have beam splitter, and the beam is divided by here, and beams go this way and this way. This is a test mass, and this beam goes both the end of the test mass.
So the beam
you can
splitter
see
is mounted on the
ground.
On the ground.
Yeah. So we can see the differential.
So at the pivot point, actually, right underneath the middle, is that right?
Yes,
But-
middle.
But on the ground, but it's attached to the ground.
Yes, it's on the ground.
So you see any seismic motion,
Yes.
the beam splitter
Yes,
shows up
exactly.
as noise. Okay.
Yes. So this is a picture. This is the vacuum tank, and here here is a laser, and beams coming like here, and here we have superconductor. And this is cooling system for superconductor. And this is the picture of the test mass. We have mirrors on the both sides for interferometers, and we have magnet for suspension. And this is the sensitivity. As I said, we can see the seismic noise here, but we think this is the coupling from the other degrees of freedom. This is coupling from seismic noise in the X or Y direction motion, and we don't have seismic isolation system, so it's kind of big.
So
One.
that coupling is presumably all coming in through your beam splitter? Motion through your beam splitter?
I don't think it's, we don't think it's coming from beam splitter, but the test mass mirrors is not completely perpendicular to these two are not perpendicular. It's not.
But you see all of the motion of the beam splitter directly,
Yes,
right?
yes.
So have you estimated what that motion is? And where it comes in?
Yes,
What's the seismic noise on the mirror would be like a pendular mode on that simple pendular mode, like this, but they are only detecting torsional mode. Only the differential motion between the two mirrors.
yeah, but it couples.
The
It couples.
beam splitter just directly.
Yes.
Yeah, but I think that would be a common mode on both.
No,
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 no.
no.
It will couple. It will couple exactly. But when we calculate the difference angle difference of two mirrors, it fits to this seismic noise. So it fits to this. So we think that this seismic noise is according to the test mass motion. And
So the test mass motion XY direction.
yeah, yes.
And it all feeds in through the magnet somehow, so the magnet gets shaken, and then down through the, so I want to say how the force gets to that.
Yes, it's this sensitivity is relativistic motion, so it depends on at lower frequencies we don't see much motion because the common mode rejection is dominant. But at higher frequencies, like above the pendulum mode, we can see the seismic coupling.
I'm skeptical. I remain skeptical.
Okay.
What is the frequency of the pendulum mode in X and Y?
This peak is the peak of pendulum mode, so 1.2 or something, 1.1 or something. Okay, and yes, and at lower frequency, the sensitivity is limited by magnetic noise. This magnetic noise comes from magnetic levitation system and also the coil magnet actuator. We don't know this exactly which is, but if we suspend the test mass with wire, this noise cannot reduced. So the coil magnet actuator is dominant also. And we did stochastic gravitational-wave search with that sensitivity. So we set a first upper limit at 0.2 Hz here. It's kind of big, but this is the first upper limit. That's the, yeah.
I think it's correct.
Yes. But this is a result of single TOBA, but for stochastic gravitational-wave search, it is not efficient to. If you see, if you observe with only one detector, it's not so efficient. So usually we use 2 detectors and perform cross-correlation analysis. So we did it. We have 2 cross sites at Tokyo and Kyoto, and we performed the simultaneous observation for about 10 hours, and we performed the cross-correlation analysis. And that sensitivity was not so good, so it doesn't change so much, only 4 times. But we expand the excluded region. So that's what we did for prototype TOBA on the ground. Another prototype is SWIM New. This is the spacecraft TOBA. It has a very small test mass bar, dumbbell-shaped test mass bar in here, and yeah, it's kind of very small one, and it will launch to space. And this worked as a rotating TOBA. And here's a picture when this SWIM was launched. This is the SWIM. It is separated from the main spacecraft.
So wait, that's not 8 centimeters, right? That's
It's whole. This is whole spacecraft. This 8 centimeter is only the what we can manage system. Yeah. So we have also some computers on the other side. So it kind of big or solar panel system. So it's kind of maybe that kind of bigger.
When was it launched?
It was launched at 2009. So it's 3 years ago. And here is the sensitivity. This is the spinning rate. The test mass is spinning with 46.5 megahertz. And so our observation band is 2 times this frequency, so around here. And this sensitivity is limited by the quantization noise into data handling, so it's not good. But still, it's the first and best space-going gravitational wave detector. Yeah. And we performed the observation for about 6 hours. And here, here is our observation band. And we set an upper limit for 2 polarization mode. Forward mode and reverse mode is the kind of mixture of plus polarization and cross polarization. So this is the first upper limit for rotating TOBA. So here is short summary for you.
So going back to SWIM, except for quantization, what would have been the next limit of sensitivity there?
This is LED.
That's basically shot noise?
Yes, shot.
Or
No, intensity noise. This is intensity noise. We don't use laser interferometer for SWIM. We have only photo sensor. It's LED is lighting, and we detect the reflection of LED light. So LED light is not so good one. So the sensitivity is bad. But
so it's not quantum now?
not quantum noise.
It's just a classical noise.
Yes, device is nice. But the problem for SWIM will be the next noise will be the magnetic coupling noise, I think. Like the spacecraft is orbiting around the Earth, so the magnetic field will change all the time. So it will be the noise. It will couple to the actuator. So it will be the noise. As long as the spacecraft is orbiting around the Earth. So here is a short summary. We propose a novel detector TOBA. The test mass bar rotates by the side force of the gravitational waves. and its fundamental sensitivity is around 0.1 to 10, 1 or 10 hertz, even on the ground. So our target is intermediate mass black hole merger or a stochastic gravitational wave background. And we already developed some prototypes, and we have prototypes TOBA on the ground. We already did principal test and search for stochastic gravitational wave background. And we also demonstrate loading TOBA as spacecraft swim. We upconverted gravitational signal, and this is the first spaceborne gravitational wave detector. So, any questions for now?
So gravity gradient noise or Newtonian noise would be a loader at low frequencies. And
Yes.
we all know Jenny loves Newtonian noise. How big of TOBA would I need at each test mass for beyond advanced LIGO to measure Newtonian noise so I can subtract out Newtonian noise? How big a TOBA?
You mean how sensitive it should be?
Yeah, sure.
So it depends on how you set the TOBA. But I don't have here. I will talk about later because Newtonian noise is kind of the next stage target. But it will be like this, like about 10 to minus 17 or something like that. So we definitely see the Newtonian noise for 10 meter TOBA. So we have to substrate Newtonian noise for gravitational wave observation, but we can set TOBA so that it is sensitive to Newtonian noise. So if so, the sensitivity is much more less. It's okay.
But could I have like a 1 meter TOBA and measure Newtonian noise?
Yeah. I will talk about it later.
Is it the same one you want? Because
So
the
problem is, don't you also measure gravitational wave at the same time when you subtract? Aren't you just subtracting everything? No?
So just make two statements. First of all, the sensitivity to Newtonian noise doesn't change at these frequencies with the size of TOBA. So if it's like 100 meter big or a centimeter big, it's the same strain sensitivity or the same sensitivity to Newtonian noise. The other thing is, I mean, this is always the same story, right? You subtract the separator channels. So if you don't.
Yeah, I thought it's better just that way. If you take this data and subtract, you will subtract gravitational wave.
Oh,
yes.
Yes, but if we set several TOBAs on the other place, Newtonian noise depends on on the location. So we can
Then you can separate.
separate. I think so. I believe.
I have a question. Has there been any analysis of coding thermal noise? Because you have these very small beams, maybe you discussed this before, but they're very, very small beams because the path lengths are so short. Do you have any idea where the coding thermal noise would fit on that curve?
Yes. I calculated for the next stage one, but it's a little bit higher. Exactly. Coding thermal noise should be a little bit higher, than the bar thermal noise. So it should be collected actually, but sorry, it's kind of old one. Yeah, but I calculated for next experiment one, so I can show you that. So, okay. Now we are proceeding to the next stage. So, but how it should be like for the next TOBA? It should be our step for 10 meter TOBA, And also, it is good if it's kind of collaborative research with interferometers. And we want some new scientific outcomes. So, we will construct 1 meter scale TOBA, and it will be cryogenic. This is the common techniques with CaJAGWR or EV interferometers. And our scientific target will be Newtonian noise, as I said. So I will a little bit introduce you about Newtonian noise. When the seismic wave or atmospheric waves comes, there are some gravity gradient. There will be gravity gradient, and this mass will be attracted to the mass and be moved. So this will be the Newtonian noise. And this is not observed yet. Still, it will be kind of problem for interferometers as like this. This is advanced LIGO sensitivity, and this we can see the Newtonian noise at lower frequencies. So, if the TOBA can detect a Newtonian noise, TOBA can be a Newtonian noise sensor. So it's kind of correlation. It will be the correlation with interferometers and TOBA. And now our key techniques for setup is about 3 we have. First, we will need vibration isolation system and decoupling. And as you see in prototype, the seismic noise limits its sensitivity. So we will make active vibration isolation table and monitor the motion of the test mass in 6 degrees of freedom and decouple the coupling and reduce the coupling. And we also have cryogenic techniques. It reduces the suspension thermal noise and burst thermal noise. And this will be correlative research with CaJAGWR and AT and so on. And I would like to propose you another option for new observation method. With TOBA, we can expand the viewing direction, and with using this, we need less detectors for doing radiometry. So this is the setup for the schematic view of the setup. We don't strictly decided, but it's like kind of like this. And we have vibration isolation table at the top. And we have a cryogenic anchor on this table, and heat shrink will come down to this. And here is the platform, and it suspends both optical table and test mass. And this is a cryogenic shield on the outside, and we have sensor box here on the optical table. And one more test mass bar can be added later, maybe. And test mass will be dumbbell shaped to increase the moment of inertia so that force noise will be reduced. And its material should be aluminum or silicon for the material research. And we have balance masses so that we can suspend as close to the center of the mass as possible. And we need vibration isolation system. As you saw in the prototype, translation motion of the test mass will couple to the rotation. Then also the horizontal seismic motion will rotate the test mass bar due to asymmetry. So we need vibration isolation system. But the performance we need is below 1 Hertz. So we will make active vibration isolation table. We put the vibration sensor on the top, and we feed back its signal to the PZT in its legs. And yes, this is vibration isolation table. And another technique is cryogenic. This is effective method to reduce thermal noise, and this is common technology with CaJAGWR and AT. So we can measure Q values of test mass or suspension, and also we can develop the methods to deal with technical problem like vibration of the cooler or something like that. So it will be good research for interferometers and 10-meter TOBAs also. And the suspension system and sensors are like this. For suspension, we suspend the both bars and optical table as optical table, so that common mode motion will reject it. And for sensors, we will use the fiber Michelson laser interferometers and monitor the motion of the bar in all 6 degrees of freedom. So suppress the coupling from the motion in other degrees of freedom. And that's our setup. So this is another option for next TOBA. So I will show you, I will talk about how we can expand the viewing direction. If gravitation, assume that bar is suspended in XY plane, and it is suspended, suspension wire is along to the z-axis. And if gravitational waves come along z-axis, the bar will rotate in XY plane. That's what I have explained before. But what happens if gravitational wave comes from y-axis? It will rotate in XZ plane. But we can observe this. We can observe this motion. So we can detect the gravitational waves from both directions. If we suspend the test mass bar near the center of the mass, the resonant frequency of yaw and pitch will be like, both will be like few millihertz or sub-millihertz. So we can detect both. So the Anton pattern function will be expanded like this. And also,
but do you need additional mirrors? Or?
Oh, we already monitored 6 degrees of freedom, so we can see this motion
or
and this motion.
interferometrically.
Yes, yes. So this is also very good for doing radiometry. If we find the plane where the amplitude of rotation is biggest, and assume that this plane is the bar is rotating, the gravitational wave should come from this plane. So we can decide the plane where gravitational source is with one detector. So it means that we need only 2 TOBAs to determine the position of gravitational wave source. So if we have 2 bars oriented to different direction, the rotating plane should be different. So the position of gravitational wave should pare down we can pare down the candidate of gravitational wave source to 2 position, and plus more. and then we consider the timing. We can determine gravitational wave source as one. It is very advantage when interferometers needs 3 interferometers to determine the gravitational wave source. And moreover, TOBA is inexpensive and small, so it is very suitable for doing radiometry and gravitational wave astronomy. And here is our sensitivity estimation. Higher frequency, this is limited by shot noise, and at lower frequency, this is the suspension thermal noise. It will be much bigger in pitch direction, but somehow like this. And the bar thermal noise or coding thermal noise, bar thermal noise is here, coding thermal noise is here, so it's bigger than bar thermal noise. And Newtonian noise is this dashed line. This is kind of preliminary thing, so we can, it's kind of hard to see, you know. So I'm trying to find how big, how sensitive can we set the TOBA to the Newtonian noise. So our future plan is with this next experiment demonstrate some techniques like cryogenics or vibrational isolation or something, and gravitational search method. And then it will go to 10-meter scaled TOBA. And also, when we can observe the Newtonian noise, the TOBA as a Newtonian noise sensor for interferometers can be developed. So this both will enhance gravitational wave astronomy. And that's all. This is a summary. We developed the TOBA for frequency gravitational wave observation, and we already developed the prototypes, 2 prototypes, small-scale TOBA on the ground and SWIM as a spaceborne rotating TOBA. And now we are planning to construct a new one. This should be our, I hope this should be our Newtonian noise sensor, and test for some techniques for 10-meter TOBA and interferometers. That's all. Thank you.
We have time for questions.
So can we go back to your last, the graph? That one? So your 1 meter TOBA is about 5 orders of magnitude away from seeing Newtonian noise at 10 hertz. Is that right?
10 millihertz.
No, 10 hertz.
10 hertz.
That's where it's relevant for Jenny.
Oh yeah. Oh yes.
So all you need to do is improve 5 orders of magnitude and and she's set.
That's true, but for now, we can, if we observe some Newtonian noise, we can set some upper limit or something to theoretical things. So it will, the first step.
So, but what could it, is there nothing you could change to shift it to higher frequencies? In
yes, yeah. It
No?
can be, it can. But at higher frequencies, interferometers is already sensitive.
So is the The microton is just a standard microton, it's not paracyclable.
No, standard.
So is there any discussion of putting paracyclic GAR into ring shot?
Yeah, we're planning to use Fabry-Perron microton, but not for now because yeah, higher frequency we don't care about. So it's enough.
I have two related questions.
Mm-hmm.
One is what the mass of the new TOBA will be, and what is the stiffness of the bar?
And the mass of the test mass. This 1 meter scale TOBA for this one is 5 kilogram or 6 kilogram or something like that. Yes.
And the stiffness?
Stiffness is thickness. Sorry, 5 centimeter.
5 centimeters.
About, it's not strictly decided, but it kind of it's on that order. Yeah.
So there's really no use to have a 10 Hertz TOBA for LIGO, really, unless you want to complete for the first detection. But because you will not use a TOBA to subtract Newtonian noise because you subtract the signal as well. So
Yeah.
that doesn't make any sense. But yeah, so I think it's more interesting for LIGO. It is interesting in a way that we learn something about Newtonian noise because it's easier to detect at these low frequencies, and so we could have relevance for advanced guidance in a direct way, but if you use it somehow to mitigate Newtonian noise for LIGO, I think that.
Yeah, in order to detect Newtonian noise at 10 Hz or something, we have to consider more further.
So this is basically Cavendish experiment, isn't it?
Yes.
So how, if you take the best realizations of Cavendish experiment and compare to this, does it reach the full sensitivity that those have, or? So another way of saying this: how well would this do at measuring big G? And could you use it as
Big.
the Newton's constant?
Newton's constant.
Yeah.
Oh yeah.
Because the Newtonian noise
yes,
is just
yes,
you
yes.
know, you take a bucket of
You can do that.
sand.
You can for the prototype TOBA, the Ando-san who is who come up with this experiment, and he already did some experiments for gravity constant experiment.
Right.
But it's not. It doesn't get better, but for this one, we can use for the gravity constant measurement. But for now, I don't think about it. But we can.
Anything else? Okay, let's thank Ayaka again. And refreshments are in the kitchen area. We've got this